Thanks very much for having me. So this talk is about genotype by the infectious environment. And of course, the genotypes we want in an infectious context is the disease-resilient genotype. So this talk is really about disease resilience. Now, all living species are confronted with infectious pathogens, so disease resilience is a hot topic for human science, animal science, plant science. My background is in animal science, so the examples I give to you are in the farmed animal species. Please don't switch off, because I think it's relevant for plants too, and I would love to hear your feedback when you tell me you're wrong in that, or this needs to be changing. But what I want to introduce today, I think, is equally relevant, and actually I would love to learn better. So about 5 years ago, Peter Knapp, many of you may know or may not know him, and we published a paper which was entitled "Why Breed Disease-Resilient Livestock and How?" And actually this paper received quite a lot of attention in the livestock community, and this is probably because Peter Knapp was research strategy manager for one of the biggest livestock breeding companies. And his key message was that you're doing it all wrong when you're breeding for disease resilience. At the moment, the way to breed for disease resilience, at least in the livestock sector, and I think it's similar a bit in plant, is to just breed for good performance in a dirty environment. So when there are lots of pathogens circulating around, you just select the animals that perform best, or the individuals that perform best in that environment. And in this paper, he warned that you may not get the desired outcome. And this is because there are two traits, host traits, that underlie disease resilience. One is the resistance, so the ability to counteract pathogen replication. And the other trait is the tolerance, and that's the ability to cope. You may be infected, but you're still coping, you're still performing well, and you're not getting sick. So there are two traits that may be antagonistically related. So, and he tried to explain this in this reactionome approach, and I know the plant breeding community is very well familiar with that. So you have two genotypes here. The blue one performs really well in a pathogen-free environment, not so well the red one, but when they're both exposed to the same pathogen burden, the red one may actually perform slightly better, despite having lower disease resistance. So one always thinks one breeds for disease resistance, but actually if you do that, you breed for better tolerance in this example. And you may tell me, okay, Andrea, this is old hat. The plant breeding community has known this for a very, very long time, and you're absolutely right. I mean, the first papers, and I was even aware of that, who pointed out about these two host genetic traits underlying disease resilience come really from the plant community. So these were published in the 1990s, early 1990s, so about 30 years from now. So you're well ahead. My message, I want to go a bit further today and say, okay, if you want to go beyond individual resilience, but you want to make your whole population resilient, so you want system resilience, you have to take another factor into account, and that is pathogen transmission. And actually, when you really start to think about it, there is no way of eradicating a disease or really preventing the big disease outbreaks without reducing pathogen transmission. And we probably don't pay enough attention towards this attribute. It's also extremely important in the era of antimicrobial resistance. You need to reduce the pathogen load in the environment. You need to protect the non-resilient individuals. So the question is not why should we breed for reduced transmission, it's how would you go about it, and especially when it's so difficult to measure. How do you measure pathogen transmission? So in this talk, I want to start a bit with the methodology, how we approach that. I want to give you some examples from disease transmission experiments. Unfortunately, they're all in livestock, but I think we can learn a few lessons. I try to draw a few lessons. And then we want to go also to field data to see how this will work in the field in the context of maybe a national eradication program. Okay, first the methodology. So how would we estimate genetic effects underlying disease transmission? What are the host traits that we need to consider? What are the models? What data do we need to collect? It's always good to look at the experts there. So reducing disease transmission is usually the job of epidemiologists, not geneticists. And the way they handle this is through the definition of this basic reproductive ratio. I think since COVID, we are all very aware of this number. The aim is to get this basic reproductive ratio of a disease below 1, and then we are fine. So we know the aim. The definition of this basic reproductive number helps us to identify the host traits that we as geneticists may be able to target. So the definition is up here. So the R0 is the expected number of secondary infection that one, let's say me, the infectious individuals, causes in a susceptible population as long as this individual is infectious for. So there are 3 host traits that underlie R0. One is the propensity to acquire the infection, so that's the susceptibility of a host. The other one is the ability to transmit the infection if you have contact, if an infectious individual has contact, so the infectivity of a host. And the third trait relates to how long the infectious person is or host is infectious for. So here I call it tolerance, and I'm quite aware about the ambiguity in the traits, but for the sake of this presentation, let's call it just tolerance, the ability to recover from the infection, how long you're infectious for. Now, 3 important aspects of these traits. First of all, like any host trait, they're likely to be under genetic control. Second, they're not that easy to observe. You know, you may be able to observe that you're infected, but you don't know, is it down to your own susceptibility, or is it because of you've just been in contact with a very infectious individual? So we're dealing with confounding here. And normally these traits are really are difficult to measure. I mean, in humans and animals, you could potentially measure, let's say, for a respiratory disease virus, the excretion. But I think for plant, it's a little bit more complicated. You could measure pathogen load on leaves or something, but often then there's a vector involved with all that or complex transmission pattern. So I think actually it's a little bit more complex even in the plant world. Okay, so now we have the traits defined. The next thing, as a geneticist, you need to define your genetic model. And here's just one example. So this is the typical polygenic, let's say, we call it the animal model, or so we have the 3 traits here, and they may be controlled by certain fixed effects, age, vaccination status, whatever. The genotype may be included as a random effect here, and we then allow that they could be genetically correlated, the 3 traits, or environmentally correlated, and we accommodate, of course, for the relationship structure, either with a numerator relationship or a genomic relationship matrix, and then some residual. So a typical model, but you could also impose different architecture, so QTL with major effects. So far, there's nothing very special, except that we have now the same model for different traits that we normally don't deal with. So we need to link now these traits to the data we can collect. And this is where we go back to the epidemiologists. They tell us how to do that. And a typical epidemiological model is this so-called SIR model. So I'm not sure if you're familiar with that, but it's actually quite a simple model. It compartmentalizes individuals into 3 states, disease states. An individual is either susceptible, then it may become infected and infectious, and then it may either be removed or die or recover. So the R stands for not contributing to the epidemic anymore. And now we need to link this model to the traits of interest, and this is here with the two key formulas. So the rate at which susceptibles become infected is called the individual's infection rate, the force of infection. It depends on a mean transmission rate that could be controlled, which type of pathogen, which environment it's in. But then this transmission rate is scaled by its own susceptibility and the infectivity of the infectious individuals it comes in contact with. So, and then this recovery rate could be, again, population or group-specific mean recovery rate, and then it's scaled by its own tolerance or recoverability or whatever trait you call it. Where we had now, this is our genetic model on there. So the traits in colors are our genetic traits. Now there are two things to point out here, which makes it very difficult to include these epidemiological models into our general mixed model framework. The first one is that it's multiplicative in the traits of interest. So it's not nicely additive. One needs to do something with that. And the other one is that it's quite dynamic, because so it sums up over all the infectious individual that this individual comes in contact with. And of course, the number of infectious individuals changes constantly, right? And I think, so here is something, I think in the plant community, this is a simpler model, but I think here you would not need to also have a spatial component, how far, because plants don't move. With animals, we just think they mingle and mix homogeneously, plants don't, so you would need to include also a spatial model here. But that shouldn't be too difficult because you know that. Right, so we have defined the model. Now we need to say, how do we link now the model, the traits, with the data we can collect? So what kind of data would we need? Well, okay, so here, this is basically if you had one individual and we model that transition between the compartments over time. Obviously, the ideal time to identify the infection rate would be to know when it become infected. And the ideal time to know the recovery rate or how long it's infectious for is the time it recovered. Unlikely you get these data, but that would be the ideal data. What we may be able to get is, though, with longitudinal data collection, with monitoring. Actually, maybe in the future with the new phenotyping tools, we'll get closer to that, right? So just to point out, now it's difficult, but that doesn't say in the future we can't do that. But the data we could potentially collect, and we have collected in experiments and field data, is repeated measurements of individuals, of their infection status. So you may go in at different time points and just check, is an individual healthy, diseased? And of course, you may take into account that the diagnostics may not be perfect, that you may not get the right healthy individuals, you may not be able to distinguish between a susceptible and recovered individual, but in principle you get some information that may let you approximate the infection and the recovery time. So these are the types of data we thought would be able to get, so everything we developed was kind of with these kind of data sets in mind. So how do we now get genetic parameters for our three host traits, susceptibility, infectivity, recoverability? So there are two approaches. One is to use the tools we have and see, can we fit that into the toolbox we have? So can we fit that into the generalized linear mixed model framework? This is actually the group in Wageningen has demonstrated that it's quite possible. So these are the so-called indirect genetic effects models for the individual's infection rates. As I pointed out before, it's not, you need to do quite some tricking and approximation to fit this dynamic and nonlinear model into a linear mixed model framework. So it relies on quite a few approximations. But the big advantage is that you can work with the tools you're familiar with, and you don't need to reinvent an entirely new toolbox. Now, the other approach is to just start from scratch and just develop the software tools yourself. And this is what we have pursued with, this is Chris Pulley, he's now working for BIOS. And we had called this software originally SIRE, Susceptibility, Infectivity, Recoverability Estimator. But now we're already in version 8, and we're going to change it to QG-EPI, so Quantitative Genetics EPI, because we want to make it much broader. But what's behind this software? So it's a Bayesian and MCMC-based inference approach. And we chose this because there's so much uncertainty in the data. You don't have the good diagnostics. There's so much you don't know. And disease dynamics is so stochastic by nature. So to us, this is really much better captured by a Bayesian framework where you can handle these uncertainties. The good thing is it requires no approximations, so you can really implement this dynamic epidemiological models. It's much more flexible, but of course it comes with all the teething problem that any new software is. Every time you apply it to new data, it doesn't work and you need to extend it. So we have published the second version with polygenic effects in the Genetic Selection and Evolution Journal, and I think we are at version 8 at the moment, which is unpublished, but it's there. We're getting there. Okay, so we validated these two approaches with simulated epidemics. So it's always good to start with simulations first. So here we used actually for your community quite a small data set, so comprising about 2,400 individuals. This is something we thought we can get for livestock or easily. We had genetic covariation in all 3 transmission traits. We had a nice population structure, so full SIPs and paternal half SIPs, so very common to many livestock species. And then we know that for estimating infectivity, we know that from our simulations, we need small groups. So we had many small contact groups. So it's kind of an ideal data set. And we assumed that we had longitudinal data of individuals' infection status without error. So this picture is Ricardo. I saw Ricardo this morning. So Ricardo is a hardcore quantitative geneticist. So he was keen to apply the conventional generalized linear mixed model framework. He was very happy there because it worked really well for capturing all the genetic variation in susceptibility. However, we did have troubles identifying genetic variation in infectivity. So we had a high failure rate. So in about 50 to 70% of runs, we got either no variation in infectivity or insanely high variation in infectivity. So we had very extreme values that they weren't right. And it didn't matter how much genetic variation in infectivity there was in the population. Regardless of that, we had a high failure rate. I think Ricardo started with a heritability of infectivity of 0.5, and the results actually for the estimates weren't that bad. So we were quite happy. So this is the true line, and this is what we got in the simulations. But the problem is it didn't scale with the genetic variance. So we just got the same variance estimate regardless of how much variance you put in. So this is just scaled by heritability here. We kept the environmental one constant. So we didn't get convincing results of the heritability for infectivity, but nevertheless, we got positive prediction accuracy, not that high, up to 0.2. So we got something, but surely you can do better. So this is in contrast the Bayesian software approach for the same scenario. So what you see here is so-called tornado plots for different simulation runs. So this shows 20 simulation runs. And the gray line, I hope you can see it in the back, this is the true value. So you can see the dots are the posterior mean estimates, and then we have the 95% credibility interval, which shows us the certainty we have in these estimates. And I hope you agree it's not that bad. So we actually, 95% of cases, we capture the true variance estimates, and the results actually seem to be quite unbiased. And the correlation for that small data set, well, of course not that accurate, but even if there's a small correlation, it tends to say there's a positive correlation. So we were quite happy with the simulated data. And in terms of prediction accuracies, so these are the accuracies for the 3 traits. So for the tolerance traits, we got a very good prediction accuracy. So did we for susceptibility. And infectivity was, of course, much harder to estimate. But it was about 2 to 3 times higher than what we got with the generalized linear mixed model approach. So we thought, okay, this is good enough to try it out on experiments. And this is where I'm going now. So there are several research questions you can approach with an experiment. And maybe the first one is that you have already a resistance marker. You have a QTL that you know confers high disease resistance or resilience, or another beneficial trait, and you want to know, does it have any effect on disease transmission? So in this case, the experiments are actually, to set up the experiment is relatively straightforward, especially after yesterday's session of experimental design. It was excellent. I learned a lot. Okay, so I want to demonstrate this with the flagship of success in the quantitative genetic, in the animal breeding world, which is infectious pancreatic necrosis virus infection in Atlantic salmon. So a few years ago, this has been a massive concern to the salmon industry. It caused very high mortality rates until they found a QTL that explains almost all of the genetic variation underlying mortality in freshwater and at sea. And of course, they selected it, so they didn't even know exactly what gene was underlying it, but they started to select on that QTL. And lo and behold, they almost managed to eradicate that disease within 5 years. So massive success stories. But I think it's valid to ask, actually, what does this QTL do? You know, because they selected on mortality after exposure. Are fish that carry the beneficial allele less susceptible? So do they not become infected in the first place? Or do they become infected and just survive better? So are they more tolerant? And what about the infectivity? So we tried to approach this with an experimental design, which was very, very simple. I mean, it's quite underpowered, but the results are quite striking. So we had, this result was only involved 300 individuals, and I think, I now forgot, I think it's 20 families. So 300 individuals from 20 families. However, they were mated and assorted depending on their resilient allele. So it was a 3x2 factorial design where we had shedder fish that carried either none of the resistance allele, 1 copy or 2 copies of that allele. And these were infected with the virus. And then they were then mixed in tanks with uninfected fish that either carried no resistance allele or just 1 copy. So it was a nice factorial, easy factorial design, and all we had as measurements is when the fish died. So we didn't have any pathogen burden or nothing. We just had when did the fish die. So we assumed our easy epidemiological model. So you see here the compartmental model that you saw before. And the aim was to estimate the genotype effect on the transmission rate, the infection rate of the susceptible individuals, and then on the death rate. So, yeah, and this is what we found. So bear with me. So what you see here in the graph is posterior distribution for the genotypic effects on the transmission, the infection rate. And you see a left graph here and a right graph. And the difference here is, on the left, we are looking at the transmission rate in the tanks of the susceptible cohabitants, and here on the transmission rates in the tanks consisting of individuals with the resilience allele. And what you see here, when you compare left to right, clearly that allele, the resilience allele, has individuals that carry that allele, their transmission rate is, or infection rate is about 10 times smaller than those that don't have the allele. So this is indication of genotypic variation in susceptibility. Now, when you look within a graph, you see 3 different overlapping distributions, colored, and that is dependent on the exposure to the shattered genotype. And you see here that, for example, the red and the blue curve, they don't overlap that much. There's a clear shattered genotype effect on when the cohabitants became infected. So that is indication for genotype-specific variation in infectivity. And it's in a good way. So if the shedders that carried the copies of the resilient allele, their transmission rate was lower. And the most surprising effect really was on the genotype effect on the mortality, because one would expect if you select for survival, you are selecting for fish that survive longer, that, once they're infected, they survive longer. But actually, our results indicated was the opposite. So if you carry that good allele, once you're infected, you die faster. So it was still, I think that it will need to be looked in better, but from deeper, but from an epidemiological context, this is perfect. So, right? So if you carry that allele, you are less likely to become infected, you're less likely to infect others, and once you're infected, you die, so you don't have so much chance to infect others. And this may well explain this massive success story. It was a small experiment, and it will need to be verified. So the question, of course, is that the exception or is that the norm? Can we always expect? Was it just a lucky case, or is that what happens? And I don't have much time to go into it. Actually, not at all. Just to tell you here, it's not the norm. We carried out other small-scale experiments, and we didn't find the same. Right? So I don't have time to go into that, but we have published these things. So the key lessons we learn here. It's actually really easy. If you have the question, what does a specific QTL do to disease transmission? It's easy to test it, but you need to test it. You cannot take it for granted that a resistance or resilience allele will reduce disease transmission. Yeah, and I'm not sure. Yeah, okay. So the next research question I want to go into is, where can we estimate these parameters? Can we do an experiment that we get genetic variation estimates and breeding value estimates for these 3 host traits? And this is an example, again, in fish, because it's easy to have a large population. And here we used a model for skin infection. And the reason why we used that model for skin infection is that we didn't need invasive diagnostics. The fish, so this was a protozoa infection, and when a fish becomes diseased or infected, it developed blisters. So we just need to observe when the fish developed blisters before they died. And the experimental design was set out. So we had 1,800 fish, so not very big, and they were distributed into 72 isolated tanks, so 72 different epidemics. And who was in the tank? So we had some inoculated shedderfish, and then we had some non-inoculated cohabitant fish. They came from different families, but the family combination in all of these tanks was matched so that we could disentangle susceptibility from infectivity. And all we had is now, when did the fish develop blisters, when did they die? We had weight of the fish at the beginning, at the end of the trial, and then we had sequence data that were, for most of the fish, but that were imputed into 1.2 million SNPs to estimate the genetic effects. Here we used our software that I introduced before. The model was a little bit, so the genetic model was a bit more complex because we had several more fixed and random effects. We had a relationship matrix that comprised genotypes and pedigree information, but in general the same as I introduced before. What was a pain, and it's still plaguing us, is that the epidemiological model is much more complex than we had anticipated, because what happens is that the fish only develop blisters. So this is so I talk you through. Fish become susceptible, then they become infected, but they may not be infectious yet. Then they may become infectious, but then they may not show it yet. And eventually they develop blisters, and then they die. So we have two latent states here that we can't observe, because we only know when they develop blisters and die. But yet we tried, so we are fitting the model with these three traits. So again, the infectivity acts now on the infectious fish and the fish that have symptoms. And the tolerance of a fish may actually act already from when it's infected. How does it cope with the infection? So when we included this model with far from perfect data, really, we still here show, this graph shows the uncertainty estimates for the three traits. So on the diagonal, you see the heritability estimates for susceptibility and infectivity. So they are, in this case, identical. They are positive and much lower than the heritability estimate for tolerance. And we actually get some unfavorable correlation, which just proves the point that you have to be careful, you have to dissect the traits. The software also allows, so we have genomic risk scores for the three traits that we can then now back transform into allelic effects. So we can do a GWAS analysis that Ricardo had carried out. And the GWAS at the moment shows that there is no exciting candidate SNP anywhere, so it's polygenic. However, there are some putative SNPs, one can go deeper. So you may say, well, okay, now you can estimate the traits, so what? How does that actually help you for the disease control? And I want to illustrate this with a very simple example. So because we can estimate the genomic risk score for susceptibility, infectivity, and the tolerance here, we can estimate a genomic risk score for the R naught. What is an individual's genomic contribution to the overall R naught? And now this is a distribution of the genomic risk score in our population. Now remember, so what could we have done if we had this before our trial? Imagine we would have known the top 20% of the individuals with the highest genomic risk score before we had the trial. Well, if we had removed them and replaced them with individuals with lower genomic risk score, this is what the contrast is. So this is on the x-axis here, you see the population-wide R naught value, which we want to bring down to 1, below 1, right? This is what we had in the experiment. So the average was roughly just below 2, and we experienced epidemics in all of our tanks. If we had removed those 20%, this is the top plot here. So in over 20% of the tanks, we would not have seen any epidemic, and the other tanks, we would have been much closer to 1. So it does really make a difference in controlling disease outbreaks. Yeah. So it's possible to estimate polygenic risk scores for these three transmission traits from experimental data. And so it's a curse and a blessing in our experiment, because the data were by far not optimal, but we still could get something. So that we learned the lesson that, yeah, they don't need to be perfect and you still get something. And again, the point is, it's good to have all these three traits because they may be unfavorably correlated. And I'm gonna skip the final case, which is, I just say a few words about it. We now, of course, want to upscale it, and one example is bovine tuberculosis. It's a big pain in the UK, as many of you would know. There's a national eradication program going on, and actually there is already a selection index that allows farmers to select cows for resistance to tuberculosis. And the question, of course, is, can we do better? Can we also breed cows that have low infectivity? So we use those data from this actually the national data are just perfect for that, because again, you have your genetic evaluation data anyway for the other traits, but now you combine it with the disease trait data, and this is exactly what they have. Once you have an infected herd, they repeatedly check every cow every 2 months until they see a positive cow, and then it gets removed. So it's the type of data we are after. At the time, our software wasn't ready to do that, so we made a simpler approach. And actually, so we identified with simpler models genetic variation infectivity. So it's a proof of concept, it's there, one could potentially breed for that. And this genetic, it's not genetically correlated with any other traits in the current indices. So that implies we are not currently selecting for high or low transmission. We are not selecting for transmission at all. So if you want to do that, if you want to select for low transmission, you need to implement it. And this brings me to the end. I think we are getting there with the toolbox for estimating the genetic effects underlying disease transmission. Evolutionary arguments would say that there is massive genetic variation in infectivity because it's not directly selected for. You don't have an advantage if you're more or less infectious yourself. So it's an untapped resource I think we should look into. But this is just the beginning. So maybe you see an application in your world. And I want to thank a lot of people who have contributed to this work here, and of course all the funders. Thank you. Sorry.